Welcome to the Probability and Statistics course. In this lesson, we are going to talk about statistical inference. Now, we have said that for statistics deals with data, how to collect data, how to analyze data in order to make conclusions about the populations that they come from. So what we are going to do now is to see how we can use probabilities, how to calculate confidence intervals, and how to calculate estimators for certain parameters of the populations using data. So we are going, as we said, to talk about statistical inference, estimators, and the central limit theorem, a theorem that is used a lot in statistics, and actually that's how we can make inference by using this theorem about our data. Now, we are going to talk in general about statistical inference, what it is about. We said that we have a population for which we want to draw some conclusions. That's the inference. Now, of course, it is very difficult or sometimes not possible to have to know everything about the population, to collect data from all population. So as we said, what we do is we collect data from a group from this population, which is our sample. So what happens is, through this sample, we make conclusions for our population, and that's what inference is. So we are going to see why we need estimation. What is estimation? The population has some parameters. We talked about these parameters. We talked, like, for example, we talked about the mean, the variance, the sample deviation, the sample standard deviation, and we said that these parameters actually are random variables. Now, from the population, we collect a sample, and what happens is that from the sample, we calculate what it is called statistic. Now, the statistic is actually an estimation of the parameters. What we do is that, because of course we cannot calculate the parameters, we do not have the population, we've got the sample, we calculate the estimators, we calculate what we think would be our parameters, and that's these we are going to draw conclusions from these for our population. So now the statistic, the estimator we calculate could be either a point estimator or an interval estimator. Now we are going first to see what is a point estimator and how it can be calculated. As we said, we have either a point estimator or an interval estimator. Both of these estimators are used to draw conclusions. We are going to see when each one is used, when each one is needed. And the point estimator actually is the estimate of the population parameter. Now, the interval estimator is an interval, as its name says, in which we can be confident at a confidence level 100 times 1 - i% is the real value of the parameter. Later on, we are going to see exactly what A is. For the moment, our confidence level, as it is called, we are going to think as how sure we are that what we have calculated is actually the true mean of the population parameter. As we said in statistics and probabilities, we deal with uncertainty. We cannot know exactly what the value of the parameter is as we do not have the population. So what we estimate, the estimator we get, is actually the value that we are going to be certain at some point that it is the true value. So, point estimator must have must satisfy some conditions. For example, we give here some condition. It must be unbiased. That means its mean value over all possible samples is equal to the true value. That means that if we repeat our experiment many times and we calculate the mean value of the estimator, then this mean value actually should be the true value of the population. It should also be efficient. That means between two estimators, we choose the most efficient one, the one with minimum variance. That means that we got an estimator which the mean value is equal to the true one, but we do not want what we get to be spread, to have the data to have a lot of spread. And also, we want our estimator to be consistent. That means its value to converge to the true value as the sample size increases. What this means is we can think as the sample size, it's how many data we have in the sample. Of course, we would expect the closest we get to the population to the estimator to give us a value more close to the true value of the parameter of the population. So in the end, if, for example, we can collect all data from the population, we actually get an estimator which its variance is 0. We have exactly the value of the population. Now, we are going to talk about the numerical descriptive measures. We have seen what these are for a sample. We have the sample mean and the sample variance. Now, when we're looking at random variables, we saw that for the population, the mean would be denoted by the Greek letter mu, and the variance here would be denoted by sigma squared. Now, we see that obviously we would have as an estimator for the mean the sample mean, the mean of our sample, and for the variance of the population, the sample variance. So what we have here is that calculating these from the data, these cannot be calculated unless they are known. We can draw conclusions for the mean and for the variance of the population from which we think that our sample comes from. So let's have a look at an example. We have collected data, which is the time to break down of 27 generators. They are, the data are in hours, And here is a table with our data. Now, first of all, we are going to make a histogram. As we have said, a histogram is a nice way to have a clear picture of maybe the distribution of the population that the sample comes from. And then we can calculate, as we said, the sample mean and the sample standard deviation or variance, which are going to be our estimators for the mean and the variance of the population. So for this data, in order to make the histogram, to see the picture, we group the data, as we said before, covering all range of data. Now, the upper points are not included, and we count how many data are in each group. We count the frequency of the data. So we have 9 data points between 0 and 50. So we make a histogram, we see the plot here, and we can understand, or we can have an idea maybe that these data come from a population that follow an exponential distribution. Now, this is not known, this cannot be certain, unless we have information that it is true, that they come from an exponential distribution, or we suspect that they come from an exponential distribution, and we need to make inference, to draw conclusions for the population from the sample. So, we suspect that the generator's data come from an exponential distribution with, we know that if really they come from an exponential distribution, the mean will be 1 over lambda, and the variance will be 1 over lambda squared. Now these values, the true mean and the true variance or standard deviation, they are unknown. We do not know what they are. But what we can do, we can calculate the sample mean, the mean from the sample, and the sample variance, the variance of our sample. So as we know, the sample mean, be careful here, this is denoted by x bar. The mean of the population is mu. The sample variance is s squared, whereas the variance of the population is sigma squared. We have to be careful with what letters we use. So we calculate the sample mean, adding up our data and divide it by 27. We had 27 data. So the sample mean for this sample was 89.52, and the sample variance is 4,673.6. Also, the sample standard deviation, we take the square root, is 68.36. Now that we have seen how to calculate, how to estimate parameters of the population using samples, we are going to see how we can put together these two and how we can actually draw conclusions for the population from this, for these parameters using the sample, the estimators of the parameters. What we have here is a very important theorem, the central limit theorem, as it is called. And this theorem tells us that if we draw a sample n from any population with mean mu and variance sigma squared, if n is large, the sampling distribution of the sample mean is approximately normal with mean mu and variance sigma squared over n. So the importance here is that we said we draw a sample n from any distribution, from any population. We do not require the population to be normally distributed. And we have that when n is large, this is important too. The sampling distribution, we mean the distribution of the sample, for the sample mean is approximately normal with the same mean as the mean of the population and the variance sigma squared over n. Now we are going to see what confidence intervals are. We talked about point estimators. We talked about the mean and the variance of a population and the sample mean and the sample variance of a sample, which are actually point estimators of the parameters of the population. Now we are going to talk about confidence intervals of these parameters that are actually intervals for which we think that the population parameter falls in with some confidence. So, as we said before, an interval, a confidence interval, is an interval in which we can be confident at a confidence level 100 times 1 minus a% is the real value of the parameter. Now, the confidence interval for the sample mean from the central limit theorem can be calculated and by using the fact that the sample mean follows a normal distribution, as we said, with mean mu and variance sigma squared over n. Now, the mean and the variance are unknown, so we're going to see how we can create the confidence intervals for the sample mean. What we have here is that we always choose a confidence level beforehand. We choose a confidence level depending on the problem we are going to solve, and also it's more experience what at the end this confidence level will be. Now, most of the times in statistics, we would use either a 90%, a 95%, or a 99% confidence interval. Now, for example, for this example, we choose a 95% confidence level. We calculate, we know that this is 100 times 1 minus a equals 95, so we need to find a, which for this example is 0.05. Now, what this is actually the area in here. The 95% is the area under the normal curve. What remains outside, as we can see, it's 5%. So this part here is 2.5% for this if we choose confidence level 95%. 5%. Now the value here of the point here of the normal distribution which corresponds to leaving out an area 2.5% is what we are going to call the ZA/2 point. Now this point, as we have seen when we saw the normal distribution, can be found in statistical tables. Now, the distribution of the sample mean is normal, as we have seen from the central limit theorem. Now, we can, as before, take out the mean, divide by the standard deviation. We remember that this will make a new random variable, which will be again normally distributed, but this time with mean 0 and variance 1. Here we remind that we divide with the standard deviation, that is the square root of the variance. That's why sigma over square root of n. And now how we can actually create the confidence interval for the sample mean is that we know that the probability that this will be between minus ZA/2 and ZA/2. These are the 2 points of the normal distribution, of the standard normal distribution. We want to use this instead of any normal distribution, we said, because we can find these points ready at statistical tables. We do not need to evaluate the probability density function of the normal distribution. That probability will be equal to 1 over A. And so if with reordering this here, leaving only mu here and bringing on the other side the sample mean, the standard deviation and the square root of n, we obtain that with probability 1 minus A, the true value of the population mean will be between these two numbers. If we substitute where these points of the standard normal distribution, if, for example, we know sigma, we know the standard deviation, and we of course know n, we can obtain this interval. Now we are going to work through an example to see actually how this can be used. All this we've learned. We have that. We assume that we have the following data. We are only going to have 4 points here. Now, here we have a small problem. We said that in order to use the central limit theorem, we have to have that the n is large. We are going to assume that we can actually solve this problem here, although n is not so large. We are going to use everything we know in order to see how we can do the calculations. But in reality, we have to be careful. We have to understand that n should be large. So if we know that these data come from a distribution which the population has standard deviation known, which is 3. We want to find, for example, let's say the 90% confidence interval for the mean. What we saw before was the 95% confidence interval. We said that we can use a 90%, we can use a 99%. For this example, we are going to use a 90%. See how we can work with 90%. Now, what we have is the normal distribution. And we want this area here to be 90% of the area. So actually, we want this together to be 10%, this area here and this area here, and half of it, we know this is symmetric, will be 5%. Now we are going to calculate the sample mean of this data. If we add up all numbers, we need a bit of space here. And divide by 4, this is equal to 190.5. Now RA, as we have seen, is 0.05. So now that we have calculated the sample mean, we know the standard deviation of the population and we know n, we can construct the confidence interval for the mean from which for the population from which the data come. So we have that. The confidence interval will actually be, this is another way, another notation for the confidence interval. These are two values. The smallest is with the minus, the largest is with the plus. And so we have, for this example, this is, we have calculated plus minus. Now for this example, we are actually looking at the 0.0, here RA was not 0.05, was 0.1. It's half, which is 0.05, and here we are looking at the point of the normal distribution at this point here. So we have that the confidence interval can be calculated here. It is known that the standard deviation is 3 over the square root of 4. And so by replacing these numbers, this can be read from the tables of the standard normal distribution, the statistical tables. and can be read. We can see that actually this is 1.645. If we do the calculations, we find that this interval is the interval 188.0325 up to 192.9675. And so this is the confidence interval for the mean from the mean we have calculated. So also we are going to see another example now. We have another set of data. We assume that a factory produces a certain product and at the end of the day measures the quantity of the production, let's say in tons. So we have the following 15 data. The data have been measured for 15 days. Change. So here we need to first to calculate the sample mean as we know for this data. It's calculated to be 125.9 and we look for the standard deviation of the sample mean. Our question is, what is the standard deviation of the sample mean? Now we see how we can use the central limit theorem. The central limit theorem tells us that the standard deviation of the sample mean is actually the square root of sigma squared from the population over n. Now, if this value is known, for example, if sigma was known to be 10, then we calculate this and it would be square root of 100 over 15, which is 2.58. And now this, the variance, the standard deviation for the sample mean can be used in order to create a confidence interval. For example, a 90% confidence interval would be 125.9, we have calculated, plus minus, we again, as before, use the 90%. So the value, the point on the standard normal distribution is the same, times this 2.58, which results in the confidence interval 121.6559 up to 130.14. Now, what we have seen in this lesson is we've talked about point estimators, we've talked about confidence intervals, we've seen how to create a confidence interval for the sample, for the mean of the of the population using the central limit theorem. The same way we can find confidence intervals for other parameters too. And that's what we are going to see in our next lesson. Here we talked about statistical inference, how to draw conclusions for characteristics of the population, of parameters of a population using a sample. We talked about estimators, point estimators and interval estimators. And we talked about the central limit theorem. We've seen how we can use in practice the central limit theorem to create interval for the sample mean, and we are going to see more confidence intervals in our next lesson. For more information for this lesson, you can visit the website of Netuno MedNetU project.